Thousands of years ago, a giant star ran out of fuel and collapsed in on itself. And in its final second, it fired two narrow beams of gamma radiation straight out into the dark. The most concentrated explosion the universe knows how to make. One of those beams has been traveling ever since, and the entire time it has been aimed at Earth. You would never see it coming. There would be no alarm, no light in the sky growing slowly brighter, no time to do anything at all. By the time the sky told you something was wrong, it would already be over. So what exactly would happen in the air, in the ocean, on your skin, if a gamma ray burst finally arrived? A gamma ray burst is the brightest thing that has existed since the Big Bang. For a few seconds, a single one can pour out more energy than our sun will release in its entire 10 billion year lifetime. Enough that, along its beam, it can briefly outshine every other star in the universe combined. We found them entirely by accident. In the late 1960s, American military satellites called Vela were watching for the gamma ray signature of secret nuclear tests. They kept catching flashes, but the flashes were not coming from the ground. They were coming from deep space. For decades, nobody knew what they were. We now know they come in two kinds. Short bursts lasting under 2 seconds are the death cries of two neutron stars spiraling together and merging. Long bursts, lasting many seconds, come from a hypernova, a rare, rapidly spinning massive star that collapses straight into a black hole. Both do the same terrifying thing. They take an almost limitless amount of energy and squeeze it into a narrow beam. And that word, beam, is the whole story. When the core of that giant star collapses, it does not explode evenly in every direction. It forms a black hole in an instant, and around that new black hole, a disk of infalling matter spins so fast and is so twisted by magnetic fields that it launches two jets straight out along the star's axis of rotation, one from each pole. These jets move at more than 99.99% of the speed of light. They punch through the collapsing star and burst out into space as two thin cones of gamma radiation, each perhaps only a few degrees wide. This is the reason a gamma ray burst is so bright and so dangerous. It is not spending its energy on the whole sky. It is spending all of it in one direction. If you happen to be standing in that direction, you receive the undivided fury of a star's death. If you are standing anywhere else, even close by, you might never know it happened at all. For 30 years, those Vela flashes stayed a mystery because gamma rays are hard to trace back to a point in the sky. That changed when we built telescopes designed to chase them. In 2004, NASA launched Swift, a spacecraft that can swing toward a burst within seconds of detecting it. In 2008, Fermi joined it, scanning the entire sky for the highest energy light in the universe. Together, they catch what earlier astronomers never could. Gamma ray bursts go off, somewhere in the sky, roughly once a day. Once a day, a star somewhere in the cosmos dies in this particular beam-shaped way. It sounds alarming until you look at where they come from. Almost every burst we record is billions of light years away, in a distant galaxy, its energy spread thin across the enormous gulf of space. From that far, a gamma ray burst is a scientific marvel and no threat at all. The danger only appears when you imagine one close and pointed the wrong way. Here is the cruelest part. The beam is made of light, gamma light, and so it travels at the speed of light. Nothing outruns it. There is no shock wave arriving first, no rumble, no warning shot fired across the bow. The radiation and the news of the radiation are the same thing, arriving in the same instant. If a burst were aimed at Earth from a few thousand light years away, the star that made it would already have been dead for thousands of years before its beam reached us. You would not be watching a countdown. From where you stand, there would be a sudden, silent flash as the upper atmosphere lit up, absorbing the gamma rays. For part of a hemisphere, the sky itself would briefly glow, and then nothing. The event would be finished in seconds. The dying, though, would take much longer. Because the real weapon is not the gamma rays touching the ground. They never reach it. Our atmosphere absorbs almost all of them high overhead. The weapon is what those gamma rays do to the air on the way in. When that much radiation slams into the upper atmosphere, it tears apart molecules of nitrogen and oxygen and lets them recombine into nitrogen oxides, the same brown, corrosive compounds that hang in smog over a city, and nitrogen oxides are catalytic poison for ozone. A single burst, lasting only seconds, could destroy a large fraction of the entire ozone layer. Some models suggest up to a third of it worldwide. And unlike the flash, this damage would not heal in seconds. The nitrogen oxides would spread around the whole planet on the high winds and keep devouring ozone for years. The flash lasts an instant. The hole it tears in our shield can stay open for the better part of a decade, and that is when the slow catastrophe truly begins. The ozone layer is the single reason complex life can survive on land at all. It absorbs the sun's ultraviolet radiation, the exact wavelengths that break apart strands of DNA. Strip away a third of that shield, and the ordinary sunlight you have stood under your entire life becomes something else. Ultraviolet at the surface could climb high enough to burn exposed skin in minutes, and, far worse, to kill the smallest organisms at the base of the food chain. The most vulnerable are the ones you never think about. The plankton drifting in the sunlit top layer of the ocean, the organisms that produce much of the oxygen you are breathing right now and feed nearly everything above them. You would most likely not be killed by the burst itself. You would be killed by the years that came after it, by a food web collapsing from the bottom upward, beneath a sun that had quietly turned against you. This is why astronomers reach for a hard word, not damage, sterilization. And we may have a case where this already happened. Around 445 million years ago, at the end of the Ordovician period, life on Earth suffered one of the largest mass extinctions in its entire history. Roughly 85% of all species vanished. It struck the shallow water and surface ocean creatures hardest, and it arrived with clear signs of sudden, brutal global cooling. In 2009, the physicists Adrian Malott and Brian Thomas laid out a careful case that a nearby gamma-ray burst fits this pattern disturbingly well. The ozone collapse, the ultraviolet stress, the way the killing fell precisely on the organisms most exposed to the open sky. There is no smoking gun. A gamma-ray burst leaves no crater, no scorched layer in the rock, nothing to dig up. It remains a hypothesis, one possibility among several for what ended the Ordovician. But it is a serious one, and it means the real question may not be whether the universe has ever pulled this trigger on Earth. It may only be how often. So should you be afraid of the night sky? Mostly no, and the reason is that same narrow beam. For a gamma-ray burst to hurt us, it has to be close, and it has to be aimed almost perfectly at Earth. And those two conditions together are genuinely rare. The famous supernova candidate Betelgeuse often gets blamed for this. But Betelgeuse is the wrong kind of star. It spins too slowly to make a burst, and its poles are not pointed at us in any case. A more serious candidate is a distant whirling pair of stars called WR104, around 8,000 light-years away, which for a time looked as though one of its poles might be aimed roughly in our direction. Later measurements muddied that picture, and today the danger looks far smaller than it first appeared. The honest answer is that the galaxy almost certainly holds no burst with our name on it right now. But the beams are out there, being fired all the time, in every direction at once. And every single day we watch another one flare and fade in the safe, immense distance. That is the strange comfort of a gamma-ray burst. Every one we detect is a catastrophe that already happened, to someone else far away, a very long time ago. A star that died before our ancestors ever looked up, its final message only now reaching a telescope. The universe fires these arrows constantly, without aim and without malice, into a darkness so vast that nearly all of them strike nothing. We survive not because we are protected, but because the sky's enormous and the beams are thin. Somewhere out there, right now, a countdown we cannot see may already be running on a star we have never noticed. If its aim is bad, we will never know it existed. If its aim is good, we still will not know, until the sky lights up, and the shot that was loosed 100,000 years ago finally lands.